Moving on to part E of this theorem, the statement of E, I've written here again. If f is less than or equal to g, then the integral of f is less than or equal to the integral of g. Recall that in this theorem, f and g are both integrable, so it makes sense to write those integrals. And this is similar to what we did in the earlier case for non-negative measurable functions. We'll first of all write g as g minus f plus f, and the reason this is helpful is because g minus f is non-negative and measurable. And by part B, g minus f is also integrable. Part D. That's part D applied along with B, where B says the integral of c times f is c times the integral of f. And basically that means that integral of g minus f, g minus f is indeed integrable, and that's g plus minus 1 times f. So that's the integral of g plus integral of minus 1 times f, which is by d with the plus, and now taking the minus out by b. So this part uses d with plus, and this part uses b, and so that gives us d with minus. Right, so that's integrable, it's the point. We can write it that way, and that's non-negative, in fact, which is really more the issue. And so what we get there is greater than or equal to the integral of f, so the integral of g is greater than or equal to the integral of f. That was pretty simple. Proof of f is kind of interesting. You might not have thought of this proof before, although after the homework, well, I don't know. Maybe I shouldn't say anything about that, depending on when you view this. So the proof of f, so f says the following: if the integral of the function f d mu over, I think I used a b there, is equal to 0 for all b in the sigma algebra, then f equals 0 almost everywhere. Now for a non-negative measurable function, we get the same conclusion if the integral over the whole space, like so, if that's equal to 0, then the function's equal to 0 also everywhere. But here we don't have a non-negative function, so we need it to be integrable over all b and a to draw the same conclusion. So in fact, we're going to use particular sets to prove this. So for our proof, the condition, the antecedent, implies that the integral of f over the set where f is positive, that's the particular b I'm going to use, like so, is equal to 0. That is, let's write that with the characteristic function now. F times a characteristic function of f greater than 0 d mu is equal to 0. Now, if that's true, what we have in hand here, like so, that thing I've underlined is a non-negative measurable function. In fact, it's actually positive. So what that says is then, by our earlier result on non-negative measurable functions, let me say it that way, since f characteristic function, f greater than 0, is non-negative, and f characteristic function of f greater than 0 is measurable, then by the earlier result, and I believe this one's in 2, 3, 4, you can check me on that, f characteristic function of f is greater than 0 is equal to 0 almost everywhere. Well, how could that be 0 almost everywhere? In fact, this is 0. F characteristic function f greater than or equal to 0 is positive on all of the set f greater than 0 on all of that set. So that means the measure of f greater than 0, that set where f is greater than 0 is equal to 0. And a similar result, you have to use a negative sign in there, but a similar result, likewise, the measure of f, the set where f is less than 0, that ordinate set is equal to 0. So the measure of the set where f is not equal to 0, just being the union of those two, is equal to 0. So you can check the little detail with f less than 0. I mean, if I were to just scribe it over what we've written down here a little bit, then let me do that and scribe it here. So if you have a less than right there, that's equal to 0. And so what I would then do is say that's not non-negative measurable. That's now a negative function, but that's okay. This is still true by part B, and now that's a non-negative measurable function. This right here, it's actually a negative function on that set, but it's non-negative measurable on the whole set, and so the same result would imply that minus with that reversed is 0, is greater than or equal to 0. Minus with that reversed is also measurable. Minus with that reversed has to be 0 almost everywhere, but it's negative on all of that set, so the set where that's less than 0 has to be 0 as well. Okay, so then G, proof of G, well, let's see what G was. G was the integral inequality. And the proof is similar to what you may have seen before. Let me write it. Let's see. Yeah. Let's see. The proof of G is write the absolute value of the integral of f d mu is equal to c times the integral of f d mu, where c equals -1 or c equals +1. Accordingly, if the integral itself is positive, c is 1. If the integral itself here is negative, then c would be -1. Yeah? So we can use either plus or minus, and if the integral is 0, it doesn't matter what we use. But by the theorem that we just, well, part C, part B, I should say. By part B, this is the integral of cf d mu, like so. But cf d mu is either plus f or minus f, and that's less than or equal to the absolute value of f d mu, since cf is less than or equal to absolute value of f with c as above, and so there it is right there. So that completes the proof of the theorem, and I think I'll stop this little clip there.